Ions are charged atoms. You learned that in chapter 2. Ions become positive, cations, by losing electrons, or they become negative by gaining electrons. They do this so they can have a fully filled or half-filled subshells, which we just talked about were stable. In the case of S and P blocks, they have an octet, fully filled S and P, like when it's all the way filled. That's like a noble gas. It has an octet, or 8 valence electrons. These are extremely stable, low energy. Isoelectric atoms are different elements with the same number of electrons. They do not have the same charge value. So let's look at electron configuration when we're looking at ionic compounds. It's the same kind of an idea. You just need to make sure when you're looking at the final electrons that you're getting them in the correct positions. And it's not that hard at all. It's what you would expect it to do, except in that one little case of being in the middle of the D block. So let's look at S or P block ionic compounds to begin with. So we're going to do one example that is a cation and one example that's an anion. So we're going to go back to sodium. We already did sodium's configuration earlier. Sodium is a metal and it prefers to become positive. So it will lose an electron. So sodium's configuration, I'm going to write it out all the way, was 1s2, 2s2, 2p6, 3s1. To make it positive, it's going to lose an electron from the highest shell, which is the 3s. So it will be 2s2, 1s2, 2s2, 2p6. And people want to write 3s0, but we don't write it. We just don't put it in at all. That's the configuration. And if that looks familiar, yeah, it does look familiar. It is the same as neon because this gives them the same number as neon. How does changing the number of electrons make a full shell? Well, in this case, losing the electron made the number, basically 8 electrons in the second energy level. How many total electrons does it have? It has 10. Notice it did have 11 and now it has 10. So let's look at an anion. So an anion, again, nitrogen, it's a nonmetal, so it prefers to become negative, so it will gain an electron. So we're going to write that neutral configuration of nitrogen. So he's 1s2, 2s2, 2p3. If we just have one negative, that's him gaining one electron, which will make 1s2, 2s2, 2p4. Is gaining one electron enough to have it fully filled P? Well, we know that our P's like to have 6, so it's not enough to do it. How many total electrons? This is 1. How many total does it need to gain? He had 3. He needs 3 total electrons to get this 2p up to 6. Does that match the number of electrons nitrogen and its column gains? Well, if we look back at any of these, remember 1 valence, 2 valence, 3 valence, 4, 5, 6, 7, 8. So nitrogen is actually right here. So it would need 1, 2, 3 electrons to get to 8. So that is consistent. So the configuration for N-3 is 1s2, 2s2, 2p6. So how many total electrons does he have? 10. Are they isoelectric? Yes. So it's that simple when you're dealing with p electrons and the outermost valence electrons being in the p or the s block. Now, if they're in the d block, there's one little thing you need to be careful with. And it's not hard, you just want to make sure you're doing it. So D blocks prefer to become positive, so they will lose an electron. Sorry, they will lose an electron. I did lose up here. D block metals have 2 very, very closely spaced 3d and 4s orbitals. So they lose and fill from the 4s before the 3d. So we're going to do an example. We're going to look at cobalt. So cobalt prefers to become positive. Again, it will lose electrons. So the neutral configuration of cobalt. So where is cobalt on one of these charts? And did we do cobalt earlier? Arsenic, vanadium. We did not do cobalt. So cobalt it actually has 7 electrons. So he's going to be like this configuration, except that it's going to be D7. He's like, let's see, 1, 2, 3, 4, 5, 6, 7. He's actually right here as cobalt. So it's argon 4s2 3d7. If we want to make it neutral, it comes out of the 4s, which might make sense to you because that's a higher out energy level, but you know, it's like saying 4s0 3d7 is what it's like saying, but don't put the 0 in. We would just say argon 3d7. Then what if I run out of s electrons? Then you start taking them out of the d. So this one would become 3d6, because with 3 electrons, 2 came from here, and then 1 came from here. Again, what are valence electrons? They're in the outermost energy levels. And make sure, if you didn't already do it, make sure that you indicated the valence electrons. So again, in this section, I'm going to use a highlighter to indicate the valence electrons. So these were together, the valence electrons. Let me go up one step. So that's the 3. So that's the valence electrons there. But then when he became Na+, now his valence electrons are here because he doesn't have the 3rd energy level anymore. Again, right here, those are his valence electrons. And I'm going to jump down to this one. These are his valence electrons. Again, they're all on that outermost 2nd energy level. So he has a total of 8. And then over here, remember we count the 3D with the 4s because the 3D are very, very close and they can do jumping around and close things like that. And then when you lose the 4s, we only have those. Those are our valence electrons right there. And if you want to work on electron configurations for everything, including transition metals, that's another Quizlet that you can work through. And as a reminder, what we've covered in this chapter, we've talked about valence and core electrons. We've recognized that valence electrons are the ones in chemical bonding. Make sure for something like sodium, you can identify the number of valence electrons. What's unexpected about copper? What about arsenic? These are all different areas of the periodic chart. Make sure that you can draw a picture that explains the Pauli exclusion principle, you know, that both electrons, they have to be opposite spins. How does the Aufbau principle explain the ordering? Remember, it goes from low energy to high energy. You build the atom from the nucleus out. Hund's rule, remember that's the bus rule, and how that guides how degenerate P, those are the same, or D, how it fills all of them. We mentioned paramagnetic, so you might try drawing both of those configurations and figure out which one is paramagnetic or diamagnetic. You can use the presence of unpaired electrons, of course, to make that characterization, so go back and check that. And then make sure, if you can use the periodic chart as a guide, you can do configurations of ions, not just of neutral elements, but you need to know the neutral elements also. Then isoelectric, and list some atoms or ions that are isoelectric.